Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, and welcome to nanoHUB-U. This is lecture 2.4, and we'll be talking about computational tools to implement the S-matrix method that we discussed in the previous lecture, 2.3. So one particular tool that we're particularly interested in is called S4. And there is also a nanoHUB tool called S4 Sim to implement this. And so what it does is kind of provide a straightforward implementation that's very general of the S-matrix method. And it can treat both refractive effects, layer to layer, as well as diffractive effects associated with periodicity within layers, within the same framework, which we discussed last time, originally developed by both Whitaker and Culshaw, as well as Tikhodev, and then subsequent researchers in the field. And it's all predicated on this idea of having these up and down modes, A and B, within each layer, which has a certain thickness, Z sub I, and allowing the user to create up to M layers, where M is in principle arbitrary, although of course we do end up limiting it somewhat. And then the detailed explanation of how this code works and kind of its intellectual progenitors or genesis is given in this paper by Victor Liu and Shanhui Fan, which came out last year in Computational Physics and Communication. And you can see the citation there. And so something that's very significant about this approach is that compared to a lot of other techniques, you actually see like pretty good convergence in terms of the accurate frequency determination of high quality factor modes. And so in particular, you see that as you increase the number of Fourier modes n, then various computational approximations of the structure will converge at different rates. But you can see in particular that some of these computational efforts start off actually quite well. So of course you can see kind of the more naive approaches, like just using kind of a direct Fourier transform can take a while to converge. It requires like hundreds of plane waves. But then if you use subpixel averaging, or if you use a fast Fourier transform, then it actually converges pretty quickly, and so there's actually not as much change. You see that the other methods gradually converge to where the subpixel calculation will start. And you can see, of course, that this code will converge if you use a sufficient number of plane waves, which is oftentimes on the order of maybe as few as 100, but maybe if you want to be particularly careful, up to about 600 to 1,000. So let me just try to walk you through briefly, like how would you set up calculation in S4. So S4 is based on this Lua scripting language. So if you haven't heard of it before, you can kind of think of it as kind of something similar to Python. And so the idea is that you'll create a new simulation, which you can call any variable you want, which you can just call S, and you call it by basically choosing the member function of the kind of the main S4 object, which is called new simulation. And then you take that object that's created, and then you gradually will add all the materials and structures that you need. First of all, like adding the materials themselves, which you give a certain name in terms of the real and imaginary epsilon components. And then you start to add physical layers that are made out of that material and also have certain thickness. And you may or may not add patterning to the layers if you care about diffractive effects like a photonic crystal. And so those patterns can have different structures and so on. And then this is just an example here where you're creating like a bunch of circles. And so then in this case, like each of the layers that you just created in which you want circles to be added, you specify the name of the layer, and then you say what material will go inside of these circles that are kind of being punched through the original material. And then you specify where the center and radius of those circles will exist. And of course, you can do this more than once if you want to. And then once you have kind of the physical geometry set up, then you're going to specify how this mode is being cited from outside. And so there are a few key variables to keep in mind. So of course, the most important thing is like which direction is the incident light coming from. So basically the way that this is specified is through kind of a polar angle phi, which goes from 0 to 180, as well as the azimuthal angle, which kind of goes around like kind of in a circle from 0 to 360 degrees. And then there's also going to be two different polarizations. In general, the S and P polarized light, which are of course orthogonal to one another. And then each one can have a different amplitude. Of course, one could be 0 if you so choose, or they could be equal. And then they may or may not have a different phase, but you have to specify the phase of each one. And then finally, of course, the frequency of the incident light is necessary. So once you have both all the specifications of the incident light, as well as the structure itself, then that allows you to then calculate the overall output. And so then this will consist of essentially using this call, in which you basically tell it you want the forward and backward power through get pointing flux. And then get pointing flux is going to look at the overall like pointing output like at a specific layer and position in the z direction. And then you can print it out using the print command in Lua. And so there are actually a whole bunch of predefined samples for you to choose from, many of which also originally appeared in the literature and can reproduce literature results in photonic crystals and other problems, even like kind of more traditional optics. And you can kind of choose from a drop-down menu like which kind of example you want to use. Or another option is there's a graphical user interface in which you can actually specify the geometry kind of using a point and click interface rather than having to memorize all the Lua commands. And so then once you have that way of specifying the geometry, then you're also able to go back and then calculate like the overall output based on a specific input waveform. Okay, and so then this is an example of the kind of output that you can get. So this is just showing the transmission through a multi-layer stack. And what's interesting is that you'll see that as you start adding more and more layers, then the transmission is going down, like over kind of the key wavelength range in which you expect to have a strong reflection. And so that also precisely matches the analytical prediction, which kind of at least validates that it correctly treats like the refractive index problem across layers. And then another thing that's important is, of course, to treat like kind of the more diffractive problems of gratings. And so if you have like a 1D square grating made of silicon and air, then you can kind of expect that there will be certain resonant wavelengths, and then there will be phono resonant line shapes, which kind of could look in general like Lorentzian or something related, in which you have like very sharply defined features. You can see in this particular case, there are actually two specific features that kind of stand out at frequencies around 0.5 and then around 0.8 in reduced units. So you kind of have those two options in some sense of how to kind of target your calculation, either in the refractive effects or the diffractive effects. Of course, you can also then try to combine those two if you want to do something more challenging. And so then this is an example from one of the original papers by Tikodiv et al., which I mentioned was one of the two seminal papers setting up this whole method when it was first started. And it shows that there can be like certain resonant peaks that are very, very strongly confined as a function of time, and basically will kind of stand out in the overall transmission of the structure. So that's of course one method. So so the point is that S4 is like a very powerful tool, and it's available on nanoHUB through the S4 Sim tool. And so the URL would be nanohub.org/tools/S4Sim. And so now I'm going to move on to another tool that's of interest, which is called CAMFR. And CAMFR actually has like a fair bit in common with the other S-matrix approach, but it's actually more based on kind of eigenmode analysis as opposed to kind of the S-matrix formulation of transfer matrices. And so again, like the motivation for CAMFR is very similar as with S4, to treat problems with layers that have different widths and have periodic structures. So the argument of the writers of CAMFR, which came out like at a similar time as the S-matrix method, is that the natural form of the solutions is actually semi-analytical in terms of eigenmodes. And so then that's what makes this a little different from the S-matrix method, because you don't necessarily do semi-analytic formulation, but you essentially solve an eigenmode problem in terms of like kind of basis functions that are kind of pre-assumed to be composed of plane waves. And so here, the basic strategy that CAMFR is going to pursue is that it's going to break structures up into a set of layers, much like S-matrix, but then it will calculate the eigenmodes associated with each layer. And in particular, you'll see in a few minutes that there will be 4 different types of eigenmodes that can be calculated. And then once we have those eigenmodes, then we would apply Lorentz reciprocity to match the boundary conditions in the problem. And so Lorentz reciprocity is important because that is kind of, I guess, a more general approach to solving the boundary condition problem than the original approach that we took of assuming that we could apply like essentially the continuity of the parallel E field and then the perpendicular B field across the boundaries. And then once we have that set up, then we can propagate within each layer of CAMFR using something that's like an S-matrix method. And then we can apply the inputs and then calculate, of course, the physical output, like the physical transmission reflection for a structure that we cared about. So let me talk about the eigenmode decomposition. So this is interesting. It's a little different from what we had before, but not extremely different. We start with a Helmholtz equation for either the E field or the B field. And you see that instead of actually solving something in terms of omega squared directly, we're actually assuming that we have omega, and then we're solving an eigen problem in terms of the beta in the z direction. But I mean, of course, it is like very analogous to what we had before, like the q squared that we showed like in the S-matrix problem. Now, we can write at this point 3D solutions for each layer. in terms of these betas that we calculate, which we can call beta k for the kth layer. And then we have this exponential for the propagation in the z direction times the initial E and H fields. So this kind of goes back to the E and B based formulation of transfer matrices rather than the up and down fields. Now, we need to, at this point, classify the 4 different types of eigenmodes, because before in the S matrix formulation, we didn't really make any attempt to distinguish between those different types. We just kind of put everything together into one framework. So now we want to look at like what's really going on in detail here. So roughly speaking, we can say that there are 4 types of eigenmodes that we can observe. And the first type would be called kind of a guided mode. And then the guided modes are shown on this kind of left-hand side region of this like complex wavelength space for the refractive index of the medium. Okay, so when basically we have like a negative effective refractive index for the medium, and then we have 0 imaginary component, then that means that it's lossless. And so it'll just kind of nicely propagate through the system in one direction. If we flip the sign and make the real part of the effective index positive, then it'll propagate in the other direction. So I guess another way to think about this is that now beta is pure real. And so this is kind of the most standard case for waveguide. And now in the other direction, we could also like write that we have radiation modes, which are kind of represented as the line along the imaginary refractive index. And so then these are like purely decaying modes. And so they decay over space and will leak out of the structure. But you can see that actually modes that are both propagating and decaying at the same time are what we kind of formally refer to as the leaky modes of the system. And then finally, there are other modes that we call complex modes. And then complex modes are kind of, I guess, analogous to the leaky modes, except they're paired into groups of 4 in this case, which have kind of like equal and opposite, like either real or imaginary parts in the effective refractive index. Now I just want to show you like what do these modes actually look like physically. And so in particular, what you see is that like these guided modes have no imaginary beta or refractive index, or sorry, I mean propagation factor. And so they kind of like tend to be strongly localized without loss. On the other hand, the radiation modes oftentimes will have like that the real part of the propagation vector beta is equal to 0. And so then these actually kind of keep oscillating throughout the structure. The complex modes that we were talking about earlier, which may have seemed a little confusing, actually kind of look similar to the leaky modes, so we can kind of group them together. And the only real difference is just that the leaky modes don't necessarily have partners that have like equal and opposite betas. But in both cases, the leaky modes are similar to the guided modes we saw earlier, except now there's also kind of this diverging component, like at the far reaches in plus or minus c, that allows some of the mode to be lost over time, which was not present in the guided mode. And so you can see that the guided modes and complex modes and leaky modes have a lot in common, except the guided mode is kind of the limiting case where the loss of that mode goes to 0. And then those are all kind of like well confined and oftentimes have like a certain like discrete frequency and resonant quality factor associated with them. But then we can see that those can all be contrasted with the radiation modes where there's not necessarily any like really strong resonance of that structure, and so it tends to kind of propagate throughout the structure without stopping. And so that kind of mode is something that may propagate very strongly in some cases, or maybe reflected just through refractive index-based effects, but not based on resonant effects. Whereas the guided modes and leaky modes all interact strongly with resonances and are usually very well defined and only happen at certain frequencies. Radiation modes can happen at almost every frequency. So that's kind of the key distinction. So in the next class, we're going to kind of go over the distinction and the development of the CAMFR approach and show how it can be used in order to get some good results. So, okay. Talk to you later.